Okay, so the next speaker doesn't need any introduction. I'm very happy to be here. I'm going to talk to you about my book on dots and lines and talk to you about networks. So I want to start off by giving an example using a memory from childhood. Maybe many of you can relate to this. I'm sure all of you at one point or another in your life have looked up at the night sky. And one of the first memories that I have as a child with my father on our farm back in Line 7 in Niagara-on-the-Lake, looking up at the night sky and seeing thousands and thousands of little dots in the sky. And of course, when you're looking up at the night sky, there are the constellations, these imagined lines which represent different things that we perceive in the night sky. So staring at this, you can see probably constellations staring at you. I'll make it a little more obvious. The Big Dipper, which is probably, I guess, the most famous of the constellations. And what is the Big Dipper? Well, it's a collection of stars out in deep space, quite deep space, as we'll see. And we're perceiving that with a light that's traveled for millions of years on our retinas and forming this pattern of this cup-like structure in the sky. But the reality is a little bit different. If you look at the Big Dipper and you look at the stars, and they're named very interesting names, at least for me when I was a child, like Alioth and Megrez, Phecta. These are the representations of the distance from the Big Dipper to us, or from the stars to us, in light years. So the amount of distance light would travel in 1 year. So very vast distances. And you can see by looking at the numbers, I mean, some of them look similar, like 81, but Alkaid on that side is 104. And if you look over here at Merak, it's 79. So they're quite far distances apart, even though to our eyes, they appear very close and very similar. So what is happening with that? What's going on? Well, there are two ways that you can look at this, and we'll talk about both ways. So the first is, in terms of networks, the sky is revealing us networks from the point of view of an embedding, which we'll talk about. Taking three-dimensional objects, these stars, and mapping them to the two-dimensional plane of the night sky. That's the first thing that we'll talk about. We'll talk about embeddings. The second is this idea that the constellations themselves, the Big Dipper or Orion or other constellations, they're collections of stars, dots, and lines that our brains graphed onto these random collection of stars in the sky. Okay, so what is a network? Well, when writing the book, I learned, as Paulina was saying, you learn lots of things. I learned that network, and I'd worked in the area for decades. Network is the amalgamation of two words, net and work. You also call them graphs, and we heard that in the last talk. And what networks are, in a nutshell, are dots and lines. So what we have, like here, we have these black dots and the lines connecting them. And it could be any combination possible, anything you could imagine. Here, what I have is, maybe you recognize this. This is Sudoku, right? A coloring of Sudoku. So if you know Sudoku, you use 1 through 9 on every row and every column exactly once, and also in these 3x3 subsquares. So this is what we call a graph coloring, and that's equivalent to a Sudoku problem. Also, most of us have flown in our life, and so we're using the airline network. So networks are pervasive. Networks come up in all areas of our life. And this is a slogan that I'll throw out. It is a slogan, but it really captures, I think, in essence, what networks do. They measure interactions. They measure interactions. So two objects, they could interact or not. One of the most basic things we could imagine. But this drives a lot of the work, a lot of the research on network science. Okay, here are two networks. They look very different. So on this side, you see this network, just a random soup of dots and lines. On this side, you see this very structured thing like a donut or torus. They actually are the same network. They're just drawn differently. So what do I mean by that? To make this drawing into this drawing, I'm not cutting any of the edges or adding or subtracting edges or adding the dots. I'm keeping all the dots and edges the same. I'm just stretching them out and moving them in different directions. So this is at its core what's happening with embeddings. Kind of like in the night sky, we have all these random stars in space. They're projected down onto these two dimensions, and they reveal this structure. Okay, so what is the essence of embeddings? There are two features that come up with embeddings. The first is a notion of a feature space, a little bit of jargon, but all it is just a bunch of attributes, right? It's just a list of attributes for whatever the dots and lines represent. So for example, you could have like a social network like this one. This is the famous Zachary Karate Club network. You could have demographics like people's age, the city they live in, their profession. If you're looking at networks in biology, the demographics could be different. There are things like biochemical properties. You could even have networks of words, which we're going to see in a little bit, and you can have their semantics or their meaning. So what you do, you have all of these attributes, but they're hidden. You don't see the attributes. You want to make a representation of those attributes. And that's what you do with embeddings. From a feature space, you project into something called a latent space. I know a little bit of jargon. That's what mathematicians tend to do, sorry, but from features, we get a latent space. And this is some space. It could be 2 dimensions, 3 dimensions, even like hundreds of dimensions, depending on what is needed, that represents the data. So the latent space, what it does is it approximates feature space. Feature space is something we don't know. Latent space is like our model, the way we represent it. And the idea, the really exciting critical idea with embeddings in this latent space, you could have a network like this embedded, say, in 2 dimensions. This is just like a drawing of a graph, a drawing of a network, embedded in 2 dimensions. And what you see, which I have with these red lines, you see possible connections between the nodes that are not there now, but could be there potentially in the future. That's called link prediction. And that's one of the key things that is used with embeddings in industry. Spotify. People here use Spotify, right? Apple Music, things like this to stream music. You notice when you're running it, you listen to a song, and after you're finished listening to the song, unless it's a playlist, it'll go to some other song. How does it choose which song to go to? Network embeddings. That's one of the tools that's used. Now, it's kind of small script. I don't know if you can see, but it creates this very long vector. I think it's like around 90 dimensions, which has all these different attributes for songs. Things like the genre, it could be like classical or heavy metal or rap. Danceability, energy, loudness, tempo, various audio characteristics. All these different attributes are associated with every song you listen to on Spotify. And they have this complicated algorithm called Musig, which is a long-winded name. But what it does is it takes songs, does an embedding, and then tells you songs you might like based on these different vectors, these different attributes that you have here. So that's one application of embeddings. Another is Uber Eats. So probably like me, especially during the pandemic, you overuse Uber Eats, right? The food delivery service, there's lots of these now. And Uber Eats also has this ability to predict what you want, recommend new restaurants, new dishes, even with the same restaurant. And they have a blog which talks about, very technical, talks about how they use network embeddings and things called graph neural networks to predict what you're gonna eat and where you're gonna order next. So network embeddings play a critical role in lots and lots of different applications in industry. Okay, so as I said, we see the night sky this way, projected down from 3 to 2 dimensions. You can also look at it in a different way. And I mentioned that earlier. From chaos, you get order. And there's this quote, very famous quote, maybe overused, but I love it, by Motzkin, that complete disorder is impossible. This drives this whole field we'll call Ramsey theory, which I'll get to in a second. All right, let me keep track of time. All right. So again, the night sky. Collection of dots and lines. We see constellations. We create this order from chaos. Let's take a look at a smaller example to understand what's happening of how we create these constellations. And I'm going to use 6 dots and all possible lines between them. So just bear with me. I'm going to explain how this works. I'm going to color the edges, 1 of 2 colors, red or blue. You can think of the blue as the lines in the constellation, for example. The red are the non-lines. So here, maybe I have a constellation which looks like kind of a cycle, right? I have all of these lines sort of drawn in. But I could also color a couple other edges red. Okay, well, big deal. If you look at this, something really interesting is happening with this. I've only done a partial coloring. I've not colored all the edges red or blue. If you look at this edge, something interesting is going on. So you could color it red, here, or blue. Only two possibilities. Do you see a red triangle? Well, yeah, there's a red triangle over there, but I don't mean that. I mean a red triangle with the different dots as the vertices. This red triangle's there. So from that coloring, just adding in that red line, I got a red triangle. On this side, adding in this blue triangle, well, I got a blue triangle, this one over here, right? So any way that I colored this, I got a red or a blue triangle. Well, maybe it's just the way I colored it. No, it always happens. So let's do a kind of proof. Let's do a mathematical proof of why this works. All right, so let's give some names to some things. Mathematicians tend to overuse things like x and k. I'm going to do that now. So let's call this vertex. We have to call it something. We call it, I don't know, Anthony or something, but let's call it x. And when you look at this, imagine all of these edges are colored. All the edges from x are colored, red or blue. Well, there are 5 edges coming out. You're going to have at least 3 red or blue coming out of x, right? Because there are 5. You split it in 2. You know, you can't do it most 2 because that would only cover 4. You're going to have 5. So what happens is, say you had 3 red, 3 blue is the same, and the endpoints there are A, B, C. Well, look at it. If any one of A, B, and C is red, we get a red triangle, right? Any one of those. So what's the only other case? They're all blue, in which case you get a blue triangle. So what we did really is we've shown that this Ramsey number, we call it Ramsey number, is 6. Well, not quite. I have to go back. If you look at 5, it doesn't work. If you look at 5, it doesn't work. So here's a coloring with 5 vertices all connected, right? Blue on the outside, all red in the middle. No red triangle, no blue triangle. You can generalize this. You can say, well, what's the smallest collection of dots and lines that I need to get 4 vertices all connected one color, no matter how I color the bigger network? That is known. You need actually 18. It's a little bit bigger than 6. And in fact, this number, we call this Ramsey number, discovered by the 20-something-year-old Ramsey, died at the age of 26. He was an economist and a philosopher. He wrote a paper on mathematical logic, which had applications, as it turns out, to networks. He discovered this whole field, which is now called Ramsey theory. And we only know those 4 values of Ramsey numbers, only those 4 numbers. In fact, R5 is one of these 4, and we don't know which. You can say, well, like, use a computer to solve it. There are too many cases. It's combinatorial explosion. We have no idea how to work with that. So here is a result that came out around the time that I was finishing up the book, or was really excited about it. You can show that this Ramsey number is no bigger than 4 to the k. This is an older result due to Erdős and Zekres. And if you've seen pictures of Erdős, this is a younger picture of Erdős, very famous mathematician, lots of papers and collaborators. He actually discovered this result in his 20s, right, in the 1930s, and along with Zekres. And there was a result that came out that improved this 4 to the k to 3.993 to the k. And when you're writing a popular math book, you're talking to non-mathematicians, as I do, we all do. They say, well, what's the big deal? You know, what's the difference between 4 and 3.993? It's a 0.007. There's a massive difference. In fact, it took, as you can see, 90 years to make this improvement. So very tough to make improvement in Ramsey theory, but there you go. Okay, networks come up all over the place. We've seen examples from the night sky, examples illustrating embedding, and also within the context of Ramsey theory. But there are lots of other places they can come up with very, very important applications that have groundbreaking advances, like Game of Thrones, right? Everybody here knows about Game of Thrones. Maybe you're watching House of the Dragon now. Game of Thrones, very, very popular show. Series of novels, George R.R. Martin. There were 19 million viewers for the finale of the show, a huge number of Emmy Awards. If you take all the characters, the legendarium, they call it, all the characters in Game of Thrones, there are over 2,000. So it's a huge collection of characters. You can form a network from these characters. If you recognize, that's Sansa Stark and Tyrion Lannister. They have an edge if they're in the same scene. So maybe in the same script, in the same scene in the show, or maybe they're a small number of words, maybe 15 words apart in the text. So you can form dots and lines from these characters. How do you visualize this network of thrones? Well, it gets a little bit more technical using this idea of the Louvain algorithm. The Louvain algorithm is not so bad. All it does is it clumps parts of the network together. So you can have a network like this where you see these clumps, red, green, and blue, and purple. And this one, which is sort of random, this one we'd say is highly modular, a highly modular network because it's split up in these clumps. This one isn't. And like Paulina said, you want to, when you're writing a pop math book, maybe limit the number of equations you had. I had this equation in a first draft, and my editor also said maybe take it out. But this equation captures this idea of optimizing modularity. And the Louvain algorithm, what it does is it takes your network, every node is in a little community, and it applies modularity optimization over and over to get it down to just a small number of communities. So do you want to see the network of thrones based on the Louvain algorithm? There you go. Now this is taken from the third book. There's a number of books, kind of like in the middle of the saga. And if you're familiar with Game of Thrones at all, you'll be familiar with sort of the characters here. And they're sort of sized up, scaled up by their importance, what the network is telling us. And again, Andrew Beveridge and Jishan, who created this, they did not actually read the book. Well, I mean, they probably read the book, but then the algorithm they used to generate this did not read it and understand it from a semantic point of view. It just extracted this network. So you're seeing people like Daenerys and Tyrion, Robb Stark, Jon Snow, all these people. They did some analysis with centrality measures, different ways of capturing things from the network. And here's what they found. No big surprise, Jon Snow is important, as you know if you've know the story. Tyrion Lannister also very important. Sansa Stark. At the beginning of the novel, she's young and she's used as a pawn. She's married off. She doesn't have very much agency in the story. But spoiler alert, as you go on in the story, she's very, very important. And network science told us this. The Game of Thrones fans were not too happy about this. They called us nerds when we came out with this thing. And it, whatever. I mean, we're not ruining the story. I guess we are a little bit. We're telling you maybe what's going to happen. But again, networks reveal this. And you see this also in things like Lord of the Rings, the Marvel Universe, Twilight, right? The vampires. And one of my students a couple of years back used this idea of embedding, which we talked about earlier, to predict character interactions. So if two characters appear in a big novel like Lord of the Rings, Game of Thrones, or Harry Potter, lots of novels all put together into one big group of text, what Vatsal could show is that after about 7 chapters, as long as the two characters have appeared somewhere in the text, even if they haven't appeared together, in 7 chapters, he could accurately predict that they'll be connected, they'll be interacting. So we can predict character interactions. So we can spoil books, I guess, using networks. Now, I don't have a lot of time. I want to keep moving things along. So maybe I'll do one more application, and that's to memes, right? I asked a student once a couple of years ago if they know what a meme is, and they said, of course, I'm 25, right? Everybody who's young enough knows what a meme is. Probably everyone knows what a meme is now. There was a pretty big meme on then Twitter I'll talk about. Anthony, you probably can't read that. It's Anthony Pompliano, no relation, okay? No relation. He put out this tweet, which you can imagine would be pretty, go pretty viral. The most successful people I've met read constantly, work out daily, are innately curious, have laser focus, and so on. You see where that's going. And you also can imagine if you're on social media that people are going to make fun of him, and they did. So Katya, the drag queen, said the most successful people that they know are dead, have passed on, or deceased, and so on. And there are literally hundreds of these that came up, as you would imagine. And here's a visualization of the Twitter sphere from Anthony Pompliano's original tweet. This is a GIF it'll go through again. From here, it starts spreading out to his contacts, and then it spreads to someone else, Sarah Ito, who retweeted it, made fun of it, and then pretty much after a few steps, it reached out to everybody and all of Twitter. There are a lot of memes now. I see my nephew in the audience who's 15, 6'7", right? 6'7" is a big one that's very popular right now. There's the 6'7" kid. What do memes do? They appear somewhere, they spread, and they seem to come up at random. We also know this from a more serious point of view, affecting all of our lives, the COVID pandemic. So what started as a breakout in Wuhan, China, and spreading out to China and Japan, over time, this is a sort of like an encapsulated time, sort of sped up all the different cases. You can start to see cases there in Italy appearing in March of 2020, and then in Iran, early cases. And then it spread when it hit parts of Europe and New York City, it was essentially game over. It spread to the whole world. So this idea of meme spreading, it's very similar in a sense to how viruses spread. And we thought of this a couple of years ago of a way of encapsulating this. And you can start with a line, right? It's like a line you're waiting in a line to go to the grocery store during the pandemic, something like this, or a line for Blue Jays tickets, whatever it is. Maybe somebody has the flu or a cold, right? That's represented by a fire here. And it spreads. It can spread sort of in front and behind. But also maybe someone else gets sick later on. It's an unfortunate line to be in, I guess. So someone else gets sick, and that's going to spread in the second round. And then eventually, in the third round, by 3 rounds, all of the network is going to get exposed to the contagion. So what we say here is the burning number, this B of this P9, we call it, is 3. And more generally, if you have a line with like n nodes, again, mathematicians and n, but if you have a general line with as long as you like, it's going to be around the square root of the number of vertices, number of steps to sort of reach everybody. And there's a conjecture. Conjecture, for those of you who don't know, it's like a vague idea that mathematicians have. They believe something is true. That if you're connected, meaning that there's a path between any pair of nodes, then the burning number is at most square root of n. It's like the worst case is a line. And we don't know how to prove this. The best known result that we have is this one. Me and a group of authors a couple of years ago, we have 4/3 n plus 1. Looks very similar, right? But that 4/3, if n is huge, like millions, billions, trillions, this is a huge difference between this and this, right? These two numbers are very different. But that's the best we know. That's the state of the art, and that's all we can do. Okay, so I'll skip over the money laundering part. Unfortunately, I don't have time, but I just want to highlight some takeaways, some things to remember about the talk, about networks. They give us a way of looking at the world, a quantitative view of the world. They're everywhere, and they measure interactions. So you can take a look at my book or follow me on X. Thank you so much.